A considerable portion of my high school trigonometry course was devoted to the solution of oblique triangles. I have still not had an excuse for using my talents for solving oblique triangles. If a professional mathematician never uses these dull techniques in a highly varied career, why must all high school students devote several weeks to the subject? By the way, non-right triangles are oblique triangles. This is none other than the much respected mathematician John G. Kemeny. However, it is the teaching and the content of school trigonometry education that has pushed us into this abyss, not trigonometry by itself. I have been particularly interested in retelling the narrative of trigonometry. So, over to the mesmerizing beauty and breadth of the apparently non-triangle trigonometry. Trigonometric functions like sine, cosine, and tangent are rooted in circular motion. They connect angles measured in radians, not degrees, to points rotating around the circumference of a circle, starting from the center, where the angle is formed at the center of the circle. The rotation starts from a fixed point on the circle's edge, called the reference point, and the center of the circle is where the angle is measured from. Sine, cosine, and tangent functions are periodic. Their values repeat after every full rotation of 2 pi radians, or 360 degrees. If the rotation continues, this repetition will carry on for infinite cycles. Also, sine and cosine are continuous for all real values in radians because the angles could assume any value on the number line, rational or irrational. It all depends on the number of cycles. For instance, a rotation of 100.5 times around the circle means an angle of 100.5 into 2 pi or 201 pi radians. The functions still give valid values for such inputs. In the previous lesson, we explored how wave motion can be represented as both periodic motion and circular motion. We discussed the advantages of using the unit circle, a circle with a radius of 1 unit, such as 1 centimeter, 1 meter, or any consistent unit of length, to represent this motion. To make full use of the unit circle, we introduced a new way to measure angles, the radian. The unit circle helps us relate the angular distance, measured in radians from the center, to the linear distance traveled by a particle moving along the circle's circumference. This relationship allows us to connect circular motion and wave motion in a precise and meaningful way. In seeing waves as circular, the reduction of the circle to unit circle thrusts an interesting change. Just one measure of change, the angular motion, or the linear distance along the circumference, is sufficient to capture the wave motion in circular form. Both are not needed. But this misses the essential construct and nature of circular motion, the two-dimensional nature of circular motion. To the point, the picture shows how circles are the result of the simultaneous action of vertical and horizontal movement around a point, the center. In a circular motion, there is continuous change of vertical and horizontal distance from the center. This characterizes circular motion. To truly represent wave motion or circular motion, we need 2 dimensions. Every point on the circle needs to be identified by 2 unique quantities, one showing its horizontal position and the other its vertical. These positions are measured along axes that meet at the center of the circle. Now think of vectors. Even though a vector's magnitude and angle uniquely define it, but for mathematical operations, we often express it using its horizontal and vertical components, just like in circular motion. That's the power of coordinates. Coordinate geometry was invented precisely to make shapes like circles, lines, and waves more amenable to arithmetic and algebra. Even complex number arithmetic and algebra become simpler when we use coordinate systems. So at this point, let's just say, when we describe circular motion using x and y coordinates, we unlock its full mathematical power. Before we dive into how x and y work in trigonometry, let's quickly revisit what it means for them to be coordinates on a Cartesian plane. The first feature is when we see x and y as coordinates, This leads to changing signs of x and y across the four quadrants of the graph. In the first quadrant, both x and y are positive, so whatever values they represent, both will be positive. In the second quadrant, x is negative while y remains positive. That means x represents a negative value and y a positive one. In the third quadrant, both x and y are negative, so both values are on the negative side of their respective axes. In the fourth quadrant, x is positive and y is negative. Here, x stays positive and y turns negative. These changing signs are a core feature of the coordinate system, and we'll apply them carefully as we move forward. But there's another important characteristic: the change in magnitude of x and y within each quadrant. This reflects the very nature of circular motion, a continuous change in x and y values as we move around the circle. Let's follow the motion anti-clockwise. In the first quadrant, x decreases and y increases. It's a vertical rise while moving laterally toward the center. In the second quadrant, x increases, y decreases. It's a vertical fall, drifting away from the center. In the third quadrant, again, x decreases, y increases, another rise, but from the lower side, moving toward the center. In the fourth quadrant, x increases, y decreases. It's a downward move, laterally returning to the right. Here, we're looking at absolute changes in x and y, that is, we're ignoring their signs. Together, these two aspects, sign and magnitude, are what make x and y so powerful in trigonometric applications of circular motion. Importantly, x and y coordinates on the unit circle can be expressed trigonometrically. Why? It's simple. In the right triangle ABC, x and y form the two legs of a right triangle inside the unit circle. If we draw a right triangle from the center to any point on the circle, x and y could be seen to represent the two non-hypotenuse sides of the right triangle. X is the side adjacent to the central angle theta, and y is the side opposite to it. The hypotenuse, of course, is the radius. And since we're in a unit circle, that's 1. So every point x, y on the circle traces a triangle where one angle is theta, the others are 90 degrees and 90 minus. This triangle moves as the point moves, and that's how circular motion becomes a right triangle in motion. This is the foundation of how trigonometry applies to wave and circular motion, a triangle spinning inside a circle. The fun begins now. The right triangle in the circle has all the sides and angles well identified. To set the trigonometric expression of the circular motion, we just have to express the moving coordinate points x and y in trigonometric terms. That is, x and y are expressed as trigonometric functions of the right triangle ABC. The picture shows how the x-coordinate is the cosine function of theta, and the y-coordinate is the sine function of theta, following the standard definitions of cosine and sine functions. Remember that we have simplified the trigonometric function expressions by making the hypotenuse the radius, that is, 1. Thus, the cosine and sine trigonometric functions are quantitatively just x and y respectively. To the point, the coordinate pair of circular motion is now trigonometric. The motion is entirely trigonometrically represented as
cosine theta and sine theta.
It would help to quickly recap why we sought trigonometry for wave and circular motion. We seek trigonometry for wave and circular motion because both are fundamentally periodic, and trigonometric functions like sine and cosine are the natural language of periodicity. Sine and cosine functions repeat every 360 degrees or 2 pi radians, just like waves and rotations. Waves, like sound or water, and oscillations, like springs or pendulums, all move smoothly, matching the shape of sine or cosine curves. Above all, trigonometric functions capture significant dimensions of change, linear as well as angular change, because trigonometry relates sides and angles. And this makes it very critical in physics and engineering. Changing angle and changing positions are waves and circle characteristic feature. To be honest, trigonometry is incredibly powerful for describing motion and change. For example, in a circular motion, just knowing the angle theta is enough to find the object's x and y positions on a unit circle. That's because cosine theta gives the x coordinate and sine theta gives the y coordinate. So sine and cosine theta directly tell us where the object is, without needing to measure curved paths or calculate distances. This is a big deal. It simplifies the math and lets us focus on how motion evolves over time. And even if the motion isn't happening in a unit circle, that is radius equal to 1, we can still use the same formulas. Just multiply sine and cosine theta values by the radius. The equations and diagrams stay the same, only the scale changes. Of course, nothing comes entirely free. Trigonometry can seem puzzling, especially when thinking about values like sine 0 degree or cosine 90 degree. But the unit circle helps resolve this beautifully. In the unit circle, we define cosine theta as the x-coordinate and sine theta as the y-coordinate of a point on the circle. So at 0 degree, the y value is 0, therefore sine 0 degree is 0. At 90 degrees, the x value is 0, so cosine 90 degrees is 0. Simple and visual, and there's more. From the right triangle inside the unit circle, we know that x squared plus y squared is equal to radius squared. No less, at the end of it all, sine, cosine, and tan are ratios, and in that case, it does not matter what the actual size of radius we are taking about, because the right triangles under different radius would all be similar. For a given angle, their ratio of corresponding sides will be the same. Henceforth, we must treat all the trigonometric proofs valid for unit circle to be applicable to all trigonometric situations. And the best news, we can recall, know, test, or prove any trigonometric identities or relationships by just thinking of the unit circle and visualizing that relationship in it. There is just one small caution here. The center of the circle must be at the origin. In that case, the circle can have any radius. Next, if cosine theta is equal to x and sine theta is equal to y, then cosine theta and sine theta values are coordinates of the circle. X and y are the coordinate points of the circumference. The picture shows the 4 key values of the coordinate points that form a circle. The picture shows the changing values of sine theta along the unit circle. As the angle theta increases along the unit circle from 0 to 2 pi radians, the value of sine theta, represented by the y-coordinate of the point on the circle, changes smoothly. It starts at 0 when theta is 0, rises to 1 at pi by 2, falls back to 0 at pi, drops to 1 at 3 pi by 2, and returns to 0 at 2 pi. This up-down-up pattern continues for every full rotation, forming a smooth, wave-like sine curve that captures the periodic nature of circular motion. The picture shows the changing values of cosine theta along the circle. The picture shows the changing values of the other ratios, tan at 4 key coordinate points. The picture shows the changing values of the other ratios, cot at 4 key coordinate points. The picture shows the changing values of the other ratios cosec at 4 key coordinate points.
The picture shows the changing values of the other ratio sec at 4 key coordinate points.
The picture shows the varying sign of the 2 key functions sine and cosine across one period, one waveform. The varying sign is very simple to appreciate when visualized in a unit circle. Recall, cosine is the length on the x-axis, the x, and sine is the length on the y-axis, the b. The sign of cosine and sine functions across the 4 quadrants follows the sign of a and b in the Cartesian plane. The picture brings out the sign of the axis in the four quadrants. And sign of the axis is the sign of the two functions. The sign of the other four functions is easily derived out of the sign of cosine and sine functions. No discussion of any function is complete without clearly defining its domain and range. Let's begin with the domain. It is the set of all valid input values. For sine and cosine functions, the input is the angle theta, and this angle can take any real number value. It could be a very small angle like 0.0234 radians, or a very large one like 24,057 radians, and even beyond. That's because multiple full rotations are always possible around a circle. So the domain of sine and cosine functions is all real numbers. The range of a function refers to the set of output values it produces for all input values within its domain. For the sine function, the output sine theta is the ratio of the length of the side opposite the angle theta to the hypotenuse of a right triangle. This ratio, calculated as theta varies over its domain, defines the range of the sine function. The same reasoning applies to the cosine function, cos theta, which gives the ratio of the adjacent side to the hypotenuse. As shown in the graph, the values of both sine and cosine functions are always between -1 and 1. This means their range is limited to the interval -1, 1. The remaining four trigonometric functions, tangent, cotangent, secant, and cosecant, are derived from sine and cosine, and their domains and ranges can be determined accordingly, often showing more complex behaviors such as discontinuities and asymptotes. The range of a function is the output values produced by the function for the input values in the domain. Recall, the output of sine theta is the ratio of the sides opposite by hypotenuse. The values of this output at all the values that theta takes is the range of the sine theta function, and similar is the case for cosine theta function. The picture shows that the range is limited to be between 1 and -1. The domain and range of the other four functions, all derived from these two functions, are rather easy to list. Sine and cosine are continuous functions as their domain and range are real numbers. The best part, they are continuous over the entire set of real numbers. This places sine and cosine as very powerful mathematical expressions for all kinds of real situations. All continuous functions that represent real situations. The importance of the continuous nature of sine and cosine functions cannot be overemphasized, and this is best seen graphically. Indeed, the next lesson is on exploring the basics of asymptotes, a graphically distinct behavior of the other four functions: tan, cot, cosec, and sec. It is critical to be convinced how the trigonometric results obtained for the unit circle are universal trigonometric identities. One of the simpler ways of understanding this is to get the real appreciation of the word unit in the unit circle. 0.5, it means 1, but that one could be any length of radius would make a unit circle. All that we have to do is to take that length as the basic unit of measurement of all lengths for that circle. Thus, if the radius is 2.8 meter, then the unit of measurement of the circle could be made 2.8 meter. That way, the radius will be 1 unit, and all the arc's lengths will be in terms of how many 2.8 meters they are. 0.25. Same is true for circles with any other radius. This is also why the trigonometric results of a unit circle are automatically valid for all sizes of circles, wave amplitudes. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.